The main difference I see when I look at the different physics APIs is kind of how they handle lifetime. When I create a body in this physics engine, what do I get back? Do I get a pointer? Do I get an index? When I get your instruction to shoot, I'm going to move other characters back to where they were 100 milliseconds ago. And then I'll pose them with the animation that they had at that moment. And then I would do the raycast. The thing that's really cool about it is determinism. That means if you rewind the game and then you replay all the same inputs, you will get the same result.
I usually like to start asking about how that you got into programming in general.
Right.
I'm pretty interested like how people started and how programming looked like then, because like right now, every 5 years, it's just like crazy.
Yeah. So I'm probably older than I look. When I was young, I was thinking about this. I wanted to know how everything worked. So I was the kid who took apart cameras, took apart toasters, whatever. And what's in there, I wanted to see how it works. So I was always going to, there's a store that used to exist in the US called Radio Shack. So I was always going there, looking at all the electronics, and they had computers there. And I also had friends who had computers. I'd see computers at the library. And eventually I managed to get myself an Atari 600 XL, which was a pretty bad computer. I feel like I made the wrong choice. I should have got a Commodore. But regardless, I learned how to program on that, using BASIC. And I made a Space Invaders game. And then I was kind of like, okay, I understand computers now. I understood memory. They had this thing on the Atari where poke and peek. And so poke is like you write to memory. Peek is you read from memory. So like I understood memory at a very young age, and I think that was very valuable to me. But then when I made the Space Invaders game, I was like, this computer kind of sucks. I had to use like a tape drive, but I was also just interested in other things like how does this lawnmower work? Or, I was going to the library and reading books about mechanical things. I actually went to undergrad for mechanical engineering. So computers were just all in the mix for me. But some interesting stories, though, about that time. So I grew up in Columbus, Ohio, and that was close to Ohio State University. So I managed to go when I was 10 years old, I went to take a computer class at Ohio State University. And this is where they had the punch cards. You could program the computer with the punch card. But then I think it was considered what they had at the time was super high tech. They had these dumb terminals that were connected to some mainframe. So as 10 years old, I don't know, I can't remember what language we were programming there, but I already knew about like loops and printing things. And so, yeah, I tinkered with that, and that was a lot of fun.
Hi everyone, let me take a break to thank members of the show who made this conversation possible. Members get earlier access to videos, including longer unedited footage from live streams, as well as they're invited to our private Discord server. If you want to support this show, there is no better way than becoming a member on YouTube or Patreon. Thank you so much. How did it happen that you ended up at the university as a 10-year-old guy?
So that was a summer class for kids or whatever that I went to. Yeah, it was like, I don't know. They had all kinds of things in the summer, like go learn to fly kites or make kites or go, here's how computers work, whatever, keep me out of trouble, I guess. But yeah, so I got exposed to computers pretty young, but still at that time, the computers were really bad and primitive. Like, this is back in the time where I would go to the library, I get a magazine, and it had a whole wall of symbols that I had to type into the computer to get the program loaded. And it wasn't just that, you had to also type in the thing that parsed the thing that you were going to type in. So I realized actually pretty young that like, oh yeah, this is going to be important. So yeah, I learned typing at a pretty young age. Going from there, my next main memory of programming when I was younger was actually when I was studying mechanical engineering. I was doing some internships and they were kind of boring. But as part of my engineering work, I got this calculator called an HP48 calculator. It's a graphing calculator, which made by HP. Back at the time, it was kind of revolutionary that you could have all these pixels that you could control on a screen. And I kind of fell in love with that calculator. It has the RPN kind of stack-based interaction. You push two numbers on the stack, and then you press plus, and then that adds them, and then that pushes the result back on the stack. So like I had this early intuition of like the stack and how this all operates. The internet existed, but there was no web pages. What we had back then was something called Usenet, which was news groups. And there was just some amazing programmers on there that documented all the assembly instructions, how the HP48 works at the bare metal level. And then there was also something called Chip 8. Chip 8 is a system. It's actually a virtual machine, but it's very assembly-like. So it's like you're writing the bytecode for a virtual machine that was kind of designed for making small games. And so that existed on the HP48 calculator. And my first thing I did there was I wrote a clone of an arcade game called Joust. And then I published that to the comp.sys.48, and then like people were all happy because now they could play Joust on their calculator. You know, they're sitting in the back of the classroom with their calculator and they're just playing some game.
How did the game got from one place to another? What did you need to do?
So the way that worked back then was there was something called UU encode, which took a binary file and converted it into text that then you could then post that text onto comp.sys HP48, Usenet. And so you would just paste that text there. It was, I don't know, maybe just a couple pages at most of text. I think what we used back then was either a parallel port or serial port on the computer, connect the calculator to that on. Back then, I think it was like IBM XT area, or maybe 286 existed. This was all kind of in the DOS era. Download that text into your calculator, and then there would be a decoder there that kind of unpacked that into a binary, and then you could run the game. So I went further. I wrote some assembly code on there, which was like, and this kind of got into 3D, where it was, you're flying through the star field, and you can kind of steer your spaceship right and left. And I was just blown away with how much faster just raw assembly code was on that system. I felt like I had unlocked like a cheat code or something. So that was just amazing. And then I I want to make my own game that kind of is my own creative effort. And I had a lot of time doing these internships. So I made a platformer game called Ant, where you're this ant and you're like in some kid's room and you're trying to get across, like, it's from screen to screen, but you're trying to get through this world to get to this empty can of Coke. So ants love Coke. So you're going through this room and there's feet stomping. There's little boulders you have to avoid. There's pits you have to jump over. So I did all the art for that. And I even put pretty bad music in there. But nevertheless, it had music. It had everything in there.
But music still on the calculator?
It was beeps.
Ah, okay.
Maybe different. I think you could control the notes, so you could play notes basically. And one of the crazy things about this is like there was no tools back then. So when I'm doing the art, I'm doing it on grid paper. I'm filling in grid paper and then figuring out what's the hex code for that.
Oh, wow.
And then and then typing in the hex code. And as I even had animations. So there's like...
Nice.
But
what tools did you use to do that? On what computer you have done that?
Right. So I was on a DOS computer, and that DOS computer, there was actually a tool that I could write normal looking chip 8 kind of assembly type of code. It looks like assembly, but it's really this virtual machine code. And there was a program called Chipper. And Chipper would take that code and then convert it into the actual chip 8 byte code. And then that byte code could be run on the calculator using this chip 8 emulator. Yeah.
Nice. That's a very extensive process. If you think about like doing first the drawing on grid paper, the animations, like each frame, then going through hex codes, then encoding it into a program. It's such a labor-intensive process just to have, you know, a couple of frames on like monochrome calculator display.
Right. So I think about that and it's like, yeah, back then, you didn't have it easy. Like if you wanted to program, you really had to want to program. Like, yeah, it was not for the faint of heart, I guess. So, but you know, I found that Usenet group very encouraging. There's people on there that were really getting into it, and it was a whole community. It was wonderful. And then yeah, I shared that game, this ant game, and then what the amazing story about that is, many years later, for my first job interview in the game industry that I actually got an offer for, that was at Crystal Dynamics. And I was being interviewed. I was not in the game industry. And back then, like, it was kind of like, are you in the game industry or not? It was like, there was like this wall, right? So it was a very kind of contained group. But nevertheless, so my interview went fine. But I think that there was still this suspicion of anyone coming from outside the game industry. But the interviewer kind of persevered and said, well, what kind of games and stuff have you made? I said, well, I did make this game on this calculator back in college. And then it turned out that the interviewer had played that game.
Nice.
And then it was like, immediately I got hired.
Nice. How many years after you made this game, this interview happened?
I think it must have been 8 years after.
Oh, wow. Okay.
So
you remembered.
The person that interviewed me had gone to school around the same time and was one of those students playing, you know, games in the back of the class on their calculator. So that's why they had played that game. Yeah.
Nice. So you mentioned at some point in the future, the time you got into the game industry was Crystal Dynamics, right?
Yes.
What happened there? Can you tell me the story? Like how did the work look like then?
So I joined Crystal Dynamics kind of at the perfect time to get into game physics because this was the PS2 era, the PlayStation 2. And this was the first game console that actually had floating point capability. The PlayStation 1 didn't actually have floating point capability, so you'd have to do all your math in fixed point. And that was not terribly appealing to me. I was very used to floating point math at that time, and I was really hoping that the computer hardware would get to the point where, oh, maybe I can do some physics work with that kind of hardware.
Can you outline how working with fixed point look like?
So fixed point It's actually possible to do game physics with fixed point. You have to, the main thing is you just have to be careful about overflow. So you need to detect that overflow. But yeah, basically fixed point is, I haven't actually done a whole lot myself with fixed point, but the basic idea is you make each value in that fixed point range, you just to say, well, this, if I increment by 1, that's going to be maybe 1/10 of a millimeter. And then that determines your range. So you always are thinking about the floating point thing at the same time, because you do need to multiply things, and the decimal point needs to move at least implicitly. So you can do all that math. You need to just define, how does your basic arithmetic work? I'm going to do addition, subtraction, and multiplication, division. Once you got those sorted out, then you can kind of just wrap that up in macros or whatever you want, and then you're kind of, you can do it. Now you can start writing your math, and things will be fairly reasonable, actually. But then, yeah, you do have to be concerned about overflow, and underflow is not as bad, but overflow would just break your simulation. So that's basically where you need to assert or something like that. You need to stop and then go figure out how to have smaller numbers. So squaring numbers, maybe you can get away with that. But then often in game physics, it's like, no, I need to cube this number, or even higher powers. And then, yeah, so you're always chasing that. So it becomes a problem of itself, and it's not as focused on the physics itself. So you're just introducing more problems in the mix, and game physics is already hard enough. So yeah.
Okay, because I mentioned crystal dynamics, but we actually have 8 years of your life in between. So if you want to highlight some of the things that were happening before these things.
Yeah, so I went to mechanical engineering for undergrad, then I did go to grad school, and I like to describe it as applied math. So I was really interested in math and still continuing to learn. So I did that, and then my first job was actually in computer-aided design. And this is a time, this was a time where a desktop computer meant you had, if you wanted to do anything serious, you had a Sun microcomputer or Silicon Graphics or DEC Alpha. My first computer, when I got my job in computer-aided design, was a DEC Alpha, and I hated that thing. It was a kind of computer where they broke all the rules to make it fast. So it didn't obey floating point standards. The software on it was really bad because it was kind of a niche thing. There was no debugger. So I managed to get myself a different computer. Actually, I think what happened was initially, back in this kind of Unix era, you could just open a terminal on somebody else's computer and do your work there. So I just asked my friend there, hey, can I connect to your Sun computer and do my work on there? So I'm just using my DEC Alpha as a dumb terminal. Anyway, so I learned a lot about kind of computer-aided design there. This was a company that was concerned with finite element analysis, where they're doing the structural analysis for cars and satellites and things like that. But then they were also doing dynamic analysis, like helicopters or, again, satellites, and trying to understand how those things moved and what kind of stresses that ultimately led to. So it was really this is engineering. You don't want to mess this up because it's going to cause some harm. So this is not real time. If we could get real time, that was great, but real time was a secondary consideration. The main consideration was, okay, let's try to get accurate results. And yeah, so that was a great experience. I did that for a while. And then I took a couple detours. This was around the time of the dot-com boom, and so everything was going kind of crazy in Silicon Valley at this time. That's where I was actually, in Silicon Valley. And so I did a little bit of the .com thing, and then I actually went into biotech for a year or two, a biotech startup. I did more kind of this physics simulation, math type of programming, optimization. We were one of those companies that was trying to fold proteins, and folding proteins is pretty hard, especially if you're gonna come at it from the angle of I'm going to simulate this thing. It's not going to work out. It's too complicated, and the timescales are crazy. You have to go down to femtoseconds, which is like 1 to the negative 12th seconds that you're marching your simulation forward. It just wasn't really feasible. So that was kind of falling apart, and it's like, okay, the PlayStation 2 is out. I love games. Maybe I love physics. Maybe now I can do it. And so, yeah, I got this job at Crystal Dynamics working on Tomb Raider, writing physics tech for them. And that kind of launched my whole kind of game physics journey. Yeah.
You knew that you want to be involved in game physics from the start.
Right. So that I can rewind a little bit for that. When I was in grad school, I got very interested in simulation of rigid bodies. And I had made a simulation there of a spinning coin or ring. And I can't show you how this works, but if you have a ring, like a finger ring, that is heavy on one side, and then you put that on a table and you spin it, you'll see that the heavy side goes to the top.
Okay.
And a friend of mine at school had shown me that, and I'm like, why does it go to the top? Because this goes back to like, I wanted to understand how everything works. So I made a simulation that showed how that works. And there was this software package that I used a lot, and I still have a lot of fondness for, called MATLAB. MATLAB is a tool for doing all kinds of numerical computations. But at that time, that MATLAB was evolving, and they had added the capability to generate a sequence of images. So I had generated a sequence of images of this spinning coin, and I pieced them together into a video. And then I gave a presentation about that, and I was thinking about this spinning coin. This looks like a video game. What if I could bring this kind of simulation into a video game? So that kind of got me thinking about that. But I knew, like, okay, this was not real time. This was done offline. I was doing frame by frame. It was super slow. But I'm like, well, maybe someday. I knew that computers were getting faster. And I'm like, okay, someday I'll have the opportunity to do these kind of simulations. So, yeah.
Okay. And the PS2 era is where the physics enters game industry, really. Because there was no like physics-based games before, right?
Right. So around that time, I think this was around 2004, you started seeing physics engines as middleware come into the scene. There was something called Math Engine. There was Novadex. There was, I believe Havoc was around then. And yeah, game physics was thought to be at that time, this is the next big thing. So we've seen these kind of things like, okay, VR is the next big thing. Back then, like physics was it. Physics was the next big thing. And so I had, just by accident, kind of got into game physics back when that was going to be the next big thing. And back then, Half-Life 2 had come out. And Half-Life 2 had shown, oh, you can make gameplay around physics. And that was such an inspiration to me. I still find that inspirational. And so I was like, I want to do that. And I'm working on Tomb Raider. I'm going to put physics puzzles into Tomb Raider. So I'm going to write a physics engine for that game that can do that. And that was like such a motivating factor for me. This is kind of get into some of my advice that I'll give later, but I want to describe for your audience, like, how did I do this? Like, how did I come onto a project, write a physics engine, and make that work? So I knew that there were open source physics engines back then. There was a open source physics engine called ODE, which was short for Open Dynamics Engine. And that still exists. It's not really used much these days, but that existed back then. It had problems. Like, you couldn't do what I wanted to do with that game, with that physics engine. But I was able to grab that physics engine and get started. So I was able to bring that code in and get started. And then I worked on, I had this knowledge from doing the computer-aided design, the protein simulation, all that. So I was bringing that knowledge in, and I used a lot of that to try to improve the Open Dynamics engine, and I basically rewrote it. So I had a starting point, and then I just rewrote it. And then by the time the game shipped, it was a completely unique physics engine. But the thing is, it got us started. We could start making things. Had something I could start working from. I could start improving. I think that is a very kind of pragmatic way to go as a programmer. Start with something and then make it your own.
Did it also lock you to a particular set of APIs, function calls, or is it you adapted them?
That's a good question. I wasn't thinking too much about APIs and such back then. I was mainly just, how do I make this game work? So my philosophy on physics engine development has changed a bit since then. It was fairly self-contained, but I believe it all just ran in the game. So you couldn't separate the game from the physics engine. But then things were simpler back then. All the code was C. You could get into the game pretty quickly, iterate a lot. But so one of the interesting things about the PlayStation 2, though, that people might find interesting is that it did have SIMD capability, and it even had a coprocessor. So what I was able to do there was I was able to write SIMD code, and I was able to set up kind of almost like a multithreading process there, where I was getting some math prepared on the main processor, and then sending that over to this coprocessor. And it was back and forth, this kind of double buffering. And so this kind of programming became possible on the PlayStation 2. And that made it actually very fast. I believe it. So when I started, I could, one of the things that physics programmers love to do is stack boxes. So I don't know why, but this is what we look at all the time is, maybe graphics programmers are always looking at shadows, whatever. Physics programmers, they're stacking boxes. So I started I stacked 3 boxes. And then by the time I had optimized all this, I had 50 boxes on the screen. And I was getting people around my desk looking oh my gosh, we've never seen so many boxes. Yeah, the PlayStation 2 was actually quite incredible piece of hardware. And they had really good tools then as well. There was this SN debugger, which is actually one of the best debuggers I've ever used. So I was able to do a lot there. But yeah, the rewriting the Open Dynamics engine, that I was doing optimizations like that, but I was also kind of working at a kind of a math level or algorithmic level. How can I how can I improve the stability? How can I improve the quality of the simulation? Back then, if you just got the Open Dynamics engine and you just want to stack 3 boxes, they would kind of wiggle and just kind of fall off. So I was like, that's not great. I want to have these nice physics puzzles and this nice kind of experience. And I knew what was possible there with Half-Life 2. Unfortunately, back then, game physics was kind of hot, but it was also very proprietary. So all the good algorithms were locked behind proprietary knowledge. So I kind of had to figure out a lot of that myself. There was some community engagement with news groups and things like that where people were talking about maybe different algorithms. So I did get some seeds of information there, but then I did go on to try to figure things out. The thing that happened then was, for me, was I was used to kind of academia and people sharing knowledge. And then I got to the game industry. I'm like, oh, I want to be part of that ecosystem of people sharing knowledge and making better games. And I think that existed on the graphics side. But on the physics side, all that knowledge was like locked down. I didn't want that to happen. I made it my goal. I'm going to change this. That was my goal. I'm like,
is this the beginning of the story of Box2D?
Yeah, this is the beginning of that. So, okay, so first of all, I had to have something to share, right? So first of all, like, okay, how am I going to make these boxes stack? And I'm going to show your audience.
Oh, wait, Box2D. Box is because of the stacking boxes.
Yes.
Such a revelation. Oh, wow.
Yeah, so there's this book.
Collision detection.
Van den Bergen.
Collision detection in interactive 3D environment.
Yes.
Okay.
So there was this book, and it actually goes along. It came out at the same time as this other book, which is also very well respected in the game physics community.
Real-time collision detection. Yeah.
Yeah. So Gino, in his book, he talks about spatial and temporal coherence, that when you're doing collision detection, you can take advantage of the fact that things are spread out, so they're not all stacked up on the one point. Things are kind of spread out, and you can make use of that to optimize things. And then there's also the concept of temporal coherence. Like in game physics, things are not moving too much from one frame to the next because they have inertia. Things are not blinking all over or teleporting all over. They're just kind of moving very slowly. Even if something looks like it's moving fast, it actually, frame by frame, it may not actually be moving that much. So I was thinking about that a lot, and how can I take advantage of that? Okay, this didn't move too much from frame to frame. And so that brought up this idea of, I know that these two boxes are touching this frame, and they're probably going to be touching again this next frame. In a physics engine, when two boxes are touching, there's something in the physics engine called a solver that's going to compute kind of the forces between these two objects. I'm going to go through a lot of work to compute those forces. Can I reuse that result for the next time step? And that's this whole idea of temporal coherence. And so I kind of ran with that idea. How can I transfer those forces forward frame by frame? And that basically, when I modified the Open Dynamics engine to have that capability, all of a sudden I could stack 3 boxes and it was just completely stable. And I was like, okay, this is the knowledge that the game physics community needs. Because up until that point, every kind of hobby project that people would do with game physics led to like this jittery jello-like mess. People would just give up, like, okay, well, I can't do anything with this. So I was like, okay, I'm going to share this knowledge because I want there to be a community of physics programmers that are sharing knowledge. And so I was like, okay, I'll go to the Game Developer Conference and I'll present this. The thing that I find incredibly amusing about all that, though, was I went to grad school. I was kind of used to conferences and what does a conference look like in applied math? It's like, okay, I write this paper and I write it in LaTeX and I line up all the math and then I put my equations on the screen and describe all the math to everyone and everyone there is like really understanding all the math and things like that. And I went to the Game Developer Conference. I'm like, okay, I'm going to present a paper called, the paper I titled it, Iterative Dynamics with Temporal Coherence, which it's totally correct. That's what I'm doing. But that's not what the Game Developer Conference is about. They're like, how did you make this game? Or like, what was the drama around my team? Or what was this war story? Or how was I crunching to whatever? So it's more about that. But so they accepted my submission, but they made me a poster session.
Okay.
So they had this thing called a poster session. So you're just kind of like, you put some posters up in the hallway and then like you show up there and people can come by and ask questions or whatever. So I went there to present my poster and there was a big crowd around me. So I don't know how that happened because like the title was so off-putting. But maybe people saw like the stacking boxes earlier and they're like, how is he stacking boxes? So
I wonder if you named it like stacking boxes ad infinitum, for example, would it be, more catchy and more deserving of a full-blown presentation?
Yeah, my marketing team was awful. So
but you say, well, do you remember what year was it? GDC?
This was 2005.
Okay, because I was told that back in the day, GDC was way more technical. And like now, GDC is more like, hey, this is how you optimize for like Steam sales and all those kind of situation. So I thought I remember GDC talks that are quite technical, at least on the graphics side and engine side and design.
You're right. It was more technical. But I think I was talking about math concepts in that presentation that are still graduate level student kind of math concepts that, most people in the game industry, they're not studying applied math. So yeah, I definitely overshot there. I think there is finding the right level of math to present at the Game Developer Conference is definitely a challenge, and that has been changing over the years. Definitely there's just a lot of things that are just not very technical these days, for sure. I think back then, yes, there was a bit more technical, like Gino from his book, he's presenting his algorithms and collision detection and things like that. And it wasn't associated with any shipping game. It's just like, here's an algorithm. These days, it's pretty hard to do any kind of presentation that's just like, here's an algorithm. Now it's like, okay, what game is this in? Or, what's the war story? What's the drama? So
the drama.
Yeah.
So you go to GDC 2005 to present your paper on temporal coherence and how to do it. And apparently there is a big crowd that wants to know about this. So that's a success, I think.
Yeah, people still refer to that paper to this day, which is kind of crazy to me. But it's on my blog, my website. So yeah, if you want to read that and see a lot of math, go for it.
Nice. I will put the link in the description after the...
Okay.
And then what happens? Is this when the Box2D is born?
So what happened was I felt like I had kind of, with that first presentation, I realized, okay, I need to make something that the audience can understand. For game developers, it needs to be two things. The math has to be broken down. You could still have linear algebra, vector math, sort of stuff like that. By that point, I had been in the game industry long enough. I knew what my peers, what were my peers understand in that industry. So I made my goal to okay, I'm going to simplify this into a digestible form that anyone can take and they could go implement. And it was a very clear recipe. And then I also thought, well, game developers, they like to see the code. Seeing the code is understanding for game developers. We want to see the code. Don't just give me some formulas. I want to see the code. So I was like, okay, what's the simplest thing I can create that will show how to implement this algorithm? So I was like, okay, I'm going to make it 2D, and it's just going to be boxes. And so the next year, I actually got into a real presentation, and I presented Box2D, and it was maybe 200 lines of code and just stacked boxes. That's all it did. I think it also had a hinge constraint. So you could have a swinging pendulum or something. And I presented that, and then I also presented something I called sequential impulses. And the idea is, okay, you got these bodies, they're stacking or whatever. You're just going to go around from point to point just applying impulses. Apply an impulse here, apply an impulse here, and then you're just going to iterate in a loop, applying these impulses. And to compute these impulses, here's some simple vector math that you do, and you can do this in a couple hundred lines of code, and you can get stable stacking of boxes. And so I felt like, okay, yeah, I reached the end of my journey of I'm going to open up game physics for everyone. You don't have to get into this proprietary engines to get this. If you want to do a hobby project, you want to write your own engine, you can do that. Here's the tech. And so that code was not supposed to be a game engine itself. It was supposed to be, here's some code, learn from it, go do your own thing. But then what happened was a year later, I came back to the Game Developer Conference and I saw, people had made games with that sample code directly. They had directly just grabbed that sample code and then made games from it. There was this game called Crayon Physics. Amazing game. It won awards and whatnot. So I realized at the time, people really want this kind of technology as an open source thing that they can use to make games. So that happened. And this kind of gets into why did I do Box2D? So that was the reason for it came into existence. It was just some sample code for a tutorial. But then it gets into why did I keep working on Box2D? Right? A lot of people, they'll make something open source and they're like, okay, I'm done with that. And I think that's totally fine. But then why continue working on it? And the reason I continue working on it is there's a couple of reasons. One was I went from Crystal Dynamics to Blizzard. After Tomb Raider had shipped, I went to Blizzard. And at Blizzard, I was going to write a physics engine for them for their console division. 2 weeks after I got there, they shut down the console division. I still, to this day, I'm not sure why they hired me. Why are you going to hire me to some division that's about to shut down in 2 weeks? I think they must have known. I don't know. But I think that shutting down that console division at Blizzard was just really okay, we need engineers for these other projects. was part of it. So I went to work on Diablo 3, which loved the Diablo games. I was so excited to be able to work on that. But they had Havoc. They were using Havoc, right? Okay, I'm on this team. I'm going to be integrating Havoc. Yeah, I can do that. And I was so, I was happy. I still got a job. I still got a job. So, okay, I'm going to do this. And, but then I've got this feeling like, okay, but I like developing physics technology for games. I want to keep growing my skills, keep growing my tool set. So how can I do that? Well, I could just do a home project, I guess. But I also want to know if it's useful. Like, is this good? Can people use this? So I just continued working on Box2D. So every time I would make an improvement, a new feature, new technology, I had like an army of QA. They think they're getting something free, but I'm actually getting something free because I'm getting
like your QA. Okay.
Exactly. Yeah. Every user is QA, and they will report bugs and say what's good, what's not. And it kind of kept that ball rolling of information sharing. Some people still continue to learn from Box2D and do their own thing. So there was that, but then there was a lot of people that were also just making their own games. So both things were happening. So yeah, so I continued developing that technology. Eventually, I got to get back to writing a physics engine for Blizzard. But then at that point, I realized developing technology for game physics in 2D is really great. It simplifies things. It's easier to debug in some ways. It's faster to develop. 3D brings in more things to consider. But on the other hand, a lot of the technologies actually translates directly from 2D to 3D. Like the data structures, the algorithms, a lot of it translates directly. So I was able to develop that technology kind of in an open way and then bring that technology into Blizzard, into their kind of proprietary engine. But at the same time, I'm getting all this kind of free QA, getting lots of exposure there. Before the 3D physics engine at Blizzard is called Domino. Before that even shipped, I'd already known, okay, yeah, this technology is working well, So I think that was very beneficial, not just to me, but it's actually beneficial to Blizzard. So they allowed me, that was really awesome that they allowed me to continue working on Box2D kind of in the public. Yeah.
But it did not become Box3D, even though there is a project called Box3D by a different author that aims to be a physics engine, I think. But why it didn't happen? Why you didn't change it into a Box3D, like to be sort of supportive of the notion that it's for both 2D and 3D?
Right, because Box2D was the open source thing. Domino was a closed source thing. And I always wanted, if I ever did Box3D, I wanted that to be open source. So if Domino were to become open source, I would have called it Box3D probably.
Okay. Yeah. But Blizzard wanted to have it proprietary in-house.
Yes.
Okay.
Yes.
Okay.
Yeah, so, it's understandable. There's a lot of, that was my job for many years, was writing the technology for that. So and they shipped lots of games with that. So I think they felt like it was a valuable thing that they had there. Yeah.
You were the only person working on that, or you had a team at some point?
So I was the main person working on it most of the time. I did have some entry-level engineers that I was training and mentoring to work on that technology as well from time to time. Yeah, so there definitely were some contributions there from entry-level engineers. But yeah, I'd say most of it was mine, yeah. Yeah.
That's wild to me, to because it seems like you're like 90 to 99% of the work behind the physics engine, and then if it's reused across a couple of games, I can imagine that like it's used in a novel way in a new game, so it like discovers some of the things that were not thought of, like not implemented or something like that. It seems like such a huge work, like physics for everything, and you still kept it. Like, can you tell me what is the challenging part of writing physics engine, or not singular one, maybe plural? Like, what are the challenging parts?
Yeah, so physics engines are very interesting because they just bring together so many different technologies and so many different algorithms. There's the math side, there's the performance side, there is the multi-threading side. I'd say the most challenging part, though, and it continues to be a challenge for all physics engine, is the solver. Like, how do you solve these interactions between lots of rigid bodies through contacts, through joint constraints? How do you do that efficiently and also be stable? There's all kinds of things fighting against that stability. If you put a 16-ton weight on top of a pebble and you want to simulate that, good luck. It's going to have problems. So there's a couple of things going on there. If I'm on a game project, say I'm on Overwatch, and somebody puts a 16-ton weight on top of a pebble, I'm just like, okay, don't do that. We'll change the content. We'll change what we're feeding to the physics engine. We will polish that content to give the best representation. That's kind of like the same thing in graphics. You make your art to suit what your graphics engine is capable of. But then there are these sandbox type of games, physics games, and they have no idea what's going to be created. So you have games like Roblox, and then there's actually a game called Sandbox from Facepunch, which is kind of like the successor to Gary's Mod. That's a sandbox game. And people love to make these kind of physics sandboxes, but then these sandboxes, you don't control what kind of things are created. And so that really puts almost unreasonable demands on what the solver can do. Because you want the solver to be real time. People want good performance. So there's incredible amount of trade-offs there. And I'm still not sure what the right trade-offs are there. It's still something I'm still researching. And nobody has, every year there's some new paper or some new thing like, oh, this new algorithm, and look how many rigid bodies I have on the screen. I have like 100,000 rigid bodies. But then you're like, okay, yeah, but the player is stacking these things in the sandbox thing, and like, oh yeah, that's not going to work. so like, if you can control the content, you can make almost any physics engine look great. But as soon as you throw it into an environment where you don't control the content, then the demands get crazy. So making those kind of sandbox games work well is still, like, nobody has solved that.
So this is also a challenge for a physics engine as a library like Box2D, right? Because you don't know what will be the end goal and use of the library.
Yeah, definitely. Box2D, and the interesting thing is, at least it used to be that most of the kind of physics puzzle games were 2D. So there was a lot of requirements there for accuracy, and actually maybe more than performance. So there's different trade-offs there. Yeah, so I would say, yeah, solvers are definitely, they'll just never be done. But then there's, okay, if I need a break from solvers, there's other problems to be worked on. one thing that's always something I'm always working on as well and trying to improve is continuous collision detection. So that's when you have fast-moving objects and you want to, because game simulation is just frame by frame, step by step, you can easily get objects to just kind of pass through each other. They need to kind of know what happened in between frames so that you can find out when they hit. And then that's actually kind of the easy part these days, is finding out when they hit. But then, like, how do you deal with that? Okay, they hit. Do I break the frame down into tiny little slices and I'm getting all these little hits in between? Okay, well, now my performance just tanked. So there's this push and pull when it comes to performance versus quality there. And it's hard to find the right balance there. Ideally, you make it somewhat adjustable, but even that's hard because you don't want to have a physics engine that has 10 different permutations of how things get solved, because how are you going to test this? How are you going to know? Like, yeah, I guess you get that army of QA out there, but still it's not a great feeling if you don't even really know yourself if it's going to work. So that's something I'm always working on. But then there's other things in physics engines that are just like, there's performance, there's the algorithms, there's the multi-threading. And that stuff is always a challenge, but it's kind of more direct. It's like, did this get faster? Yes or no? Okay, done. So it's kind of very easy compared to like, okay, is this solver just right? It's hard to know.
I was wondering, because you have worked a lot in this area, is there like a great physics API? Most people will interact with physics engines through an API of some sorts. Most people will not raw dog their own physics. They will use like something off the shelf. Is there a better API and a worse API, or is it sort of similar for most of it? Because I think, as far as I understand, like most physics engines have quite similar API, right? You can have like joints, you can have constraints, you have some geometry types like vectors and matrices, and like you can have velocity and like acceleration. Is there something that's easier to work with that you found?
Yeah, I think you're correct. If you kind of round up all the physics engines and see what do they do, how do you interact with them? Yeah, you're going to be creating rigid bodies. You're going to be adding collision shapes to those rigid bodies. You're going to have a world or a scene that kind of owns all those things. And then that scene, you're going to kind of be marching forward in time. You'll be doing raycasts against that scene, all kinds of collision queries. You'll want to know, did these two things just start touching? Did they stop touching? How are they touching? There's all those kind of features. Any competent physics engine is going to have those kind of features. So you don't really have there's not a whole lot of, there is always things that you can add around the perimeter that are different. For example, maybe I'll give support for explosions or wind or buoyancy or things like that. Those things around the perimeter you can certainly add. I think the main difference I see when I look at the different physics APIs is kind of how they handle lifetime. When I create a body in this physics engine, what do I get back? Do I get a pointer? Do I get an index? Do I get a handle? And then how is that thing live? Do I have to free it, or do I decrement a reference to it? Do I get an event when something else destroyed it? I get a callback. And I've dealt with that a lot. One of the interesting things working at Blizzard was I had this physics engine that I had to integrate into several projects. And a lot of the time I'm doing that integration work. And I was thinking, well, how can I make my life as integrating this easier? So I settled on, finally for Box2D, you can see this approach, which is kind of a very flat kind of C API. And what you're getting back are these kind of opaque handles. And these opaque handles, you'll never get a callback to say this handle is invalid or there's no reference counting. Instead, what can happen is this handle you can always ask, is this handle valid? And then the physics engine can tell you, oh yeah, that thing got freed. So you would you can either immediately just check, is it good before I make a function call with it? Or if I make a function call with it, you'll get, and it's orphaned, you will get an assert. So with pointers, you can't do any of that. Is this pointer still good? It points to some data. So you can implement these handles in many ways. Sometimes people will embed a pointer in the handle and maybe some other data. I ended up doing it. The handles, basically, the handle embeds an index to the world that it belongs, like for a body, say. I have a body ID. The body ID embeds an index to the world it belongs to, an index for the body itself, and then a special number in there called a generation. And that allows that index to be reused. And every time that index is reused in the physics engine, that generation number internally gets bumped. So if you bring back your old ID, I would check the world, check that index exists, and then at that index, I would check, okay, what's your generation on this? And then I can easily just detect this has gone bad. This is especially tricky in a physics engine because I have bodies, and then I have shapes on those bodies, and then I have joints connecting these bodies. If I delete the body, what happens to the shape handle? Where's the shape? Well, the shape should probably be destroyed if the shape on that body got destroyed. The body got destroyed that owns it. And then joints, they connect two bodies. If I destroy one of the bodies, what should happen to that joint that's connecting these two bodies? My take is that that joint should no longer exist. It should become invalid because I don't want people interacting with that thing thinking that they're doing meaningful work when nothing's going to happen. So this kind of ID generation system has worked really well. And then also I think that there's other things about the API. I think having a C API is really valuable. The reason is because it can be easily just wrapped by any programming language, right? So the physics engine can work, you can wrap it and you call it from C#, or you could call it from Rust, or you could call it from whatever. And that's kind of easier. And then another thing about the C API is I can have a lot of my internal data structures just out of view. So I'm free to change those things and optimize things without breaking a lot of the user's code.
Nice.
Which, yeah. In C++, it's just kind of, you just see everything, or you need some sort of pointer in there, and I don't know, and it's harder to wrap. So yeah, the C++ I don't think is very good for APIs.
Nobody likes C++ APIs. Everybody's like, oh, give me C API, and then I can do anything with it. Like C++ is like, oh, but like, do you do this? Do you use this? Do you use templates? Do you do that? It's like so many questions.
that kind of gets interesting because an older version of Box2D was a C++ API. And that kind of got into that kind of language noodling sort of thing. Like, why don't you make this thing a template? Or could you modernize this C++? Why don't you use this other C++ feature? And I was like, like I don't want to be noodling on language things. I got other problems to solve here.
I think this is something that's very interesting, that like C++ involves in making so many of these decisions that are adjacent to what you're actually doing. And people have so many flavors of, oh, we can do it this way or that way or this way plus this way, but not this way. And this never-ending discussion. As far as I understand from Box2D, you are like a C API enjoyer, meaning like very simple function calls, and data structures is a collection of data members in a struct, and like we don't worry about like, you know, whether it's private or what's the getters or setters or whatever.
Yes. Yeah. I mean, that's something I kind of like about the C APIs is like, if you want it to be private, like truly private, just don't put it in the header and you're good. Like it's somewhere in your source folder. With C++, people are just, oh, I'll do private. But that's such a like, you're still making the other person compile this thing. I don't want to compile this thing that I can't, it's not something for me to interact with. I'm just paying for the time to compile. That's another thing is the C API. Like when your files that include that C API, they're not going to be slowed down by including that C API when you're compiling them. I once saw a physics engine that was purely header files and it was all templates. And I'm like, okay, I'm going to use your physics engine and I'm going to pay for it every day. And I'm compiling.
Now, tell me in what state Box2D is now? Since the development started way back, what is it now?
Yeah, so Box2D is kind of had an interesting history. There was a big push in the beginning because I wanted to solve a lot of the technology problems that I was hoping to solve for Blizzard games. And then it kind of didn't get much attention for quite a while. I would fix bugs maybe once a year or something like that, but I wasn't really pushing on features.
Okay.
It would be like spring break or something like that. Okay, I'll check out Box2D and fix some bugs. But on the other hand, the previous version, for what it was stable. It was mature. But then what happened a few years ago was, so I got my current job and I decided that maybe I'll be writing some new physics tech for this current job. And I needed to do better about performance. The previous version of Box2D was still trying to be pedagogical. You know, it's like, oh, I can take this, I can learn from this. And from that point of view, introducing a bunch of multi-threading there or other kinds of optimizations that maybe become harder for a junior level programmer to really kind of understand, or a hobbyist. I didn't want to do that, but as I decided, okay, well, that thing, it still exists. Like you can get this older, more easier to understand, readable sort of thing. I even have something called Box2D Lite, which is that original tutorial that you can go back to and then like, okay, here's the simplest thing, learn from this. But I decided, okay, I want to now, for my own interest, but also because I thought I might need to develop some more tech for my current job, I was like, I'm going to make this thing fast. Okay, I am going to do whatever it takes to make this thing incredibly fast. And so I got into all the multi-threading, I got into the graph coloring, I got into, making things very kind of data-oriented, very array-based. And I learned a lot there. It was a very rewarding experience. Yeah, and then I took a detour. At one point, I was like, okay, I need to make the solver better. But what happened was I had all this performance machinery around the engine at that point. It made it harder to try to I want to try 20 different solver algorithms. I want to compare, I want to be objective. Let's just compare all these. But I didn't want to do that in Box2D because there was already a lot of kind of built-in assumptions there. So I created this other project called Solver2D. And I implemented, it must have been about 8 different solvers or so. And you could run the simulation, it had visualization, and you could draw all 8 solvers running simultaneously on top of each other. And you can see, okay, yeah, this one stacks boxes more stable. This one, the boxes fall over, things like that. Or this thing was unstable, this one was stable. So yeah, it was very interesting little side project. It's still there. It's open source, but it's not something anyone would use. But it was kind of interesting because I got that to a point where I was like, okay, I have a good set of comparisons here. I'm just going to make a YouTube video and just kind of ramble about this stuff for 45 minutes. I'm just rambling about these different solvers and comparing them. And then a lot of people watched it. So it was, I guess it was valuable. I think it's cool because it's there. If I ever get a different solver idea, instead of tearing up Box2D, I can just go implement over there. And in Solver2D, there's no concern for performance. The feature set is kind of minimal. It's easy just to kind of plug something in there and try something new. That was an interesting detour. So getting back to Box2D, I'm still working on improving performance. And I think it's getting pretty mature now. It's on version 3.1. Version 3.2 I will probably take a break after that. That's the next version coming. And there I'm trying to have some more features that people have really just been wanting for a very long time. People, and some of these features have gone into the latest version. Some people want to say, I don't want to be constrained to a world that's 20 kilometers across. I have big ideas. I'm going to make a big game. I need to go out to 100 kilometers or 1,000 kilometers or 10,000 kilometers. So I've added the capability to represent the position of the body with double precision. But then everything else internally in the simulation is single precision. And the way that works is once you get to the math, like colliding these two shapes or applying impulses between these two things, that's all done in relative coordinates, all in single precision, all that math. So that keeps the performance very high. Some people will just say, oh, I'm going to get this physics engine and I'm just going to flip all the floats to doubles and then I'm done, right? Everything is doubles now. But then that's such a, why do I need doubles for rotation? How fine do I need to understand the angle of this thing? It doesn't make any sense to me for most cases. So for that feature, I really wanted it to have full performance. And one of the things that's in Box2D that makes it fast is I have, for a lot of the math in the solver is done with SIMD. Like the heaviest math is done with SIMD. And it's a kind of SIMD that it's hard to accomplish, but it's very valuable. And that's this idea of wide math or wide SIMD, where it's not just that I have a vector and I'm going to put that into SIMD. No, it's more like I'm going to solve 4 constraints at a time. And each SIMD vector is actually like, these are my x's for one SIMD vector. These are my y's for another SIMD vector. These are my z's. So I have 3 SIMD vectors, and then I'm doing math on those. And that unlocks a lot of performance. And so with the double precision, then maybe you could do 2 constraints at a time, but then I'd have to rewrite all that stuff. That was not interesting to me. I'm just going to do the math in relative space, and I'll keep all that performance. Yeah. So there was that. So that's kind of like this large world support. And then another thing that's gone in recently, it's still developing, is so I put in this ability to record the simulation to a file and then load that simulation back into a viewer. So if you have a game, you have some issue with it, you can generate a recording and then load that into the viewer and see that. But then as part of that process of creating that system, it gives the ability to take a snapshot of the world, and then you can restore the world to that snapshot.
Oh, that's so cool.
And so that's cool. You can rewind time for your game now. The thing that's really cool about it is determinism. So that means if you rewind the game and then you replay all the same inputs, you will get the same result. And that's cross-platform. So you will get the same results on Mac or Windows or Linux. And there's no performance sacrifice for that determinism. Yeah.
Because all of the math happens in a floating point, the standardized version of floating point, 32 bytes, or why is that the case?
So, yeah, I wanted to talk about this a little bit. Determinism. There's a lot of confusion around determinism in game development. It used to be the case in the 32-bit era that you really couldn't get any kind of cross-platform determinism, cross-compiler determinism. You would just have to go to fixed point. And a lot of games like StarCraft, with this peer-to-peer networking, has to be fixed point for that era. These days, in the 64-bit era, you can just tweak a few things and you can get completely floating point deterministic code. And the things that you need to do are not too difficult. One, you have to turn off, on Windows it's called fast math, and then on Linux it's called contractions. Basically, on Windows, the fast math option allows the compiler to remix your math, but then it also allows the compiler to introduce these FMA or fuse multiply add instructions. These fuse multiply add instructions, they have this problem where internally they would do math at a higher precision and then round a result at the end. This is a real problem because if you have a computer that doesn't have that SIMD instruction, or you disable that SIMD FMA instruction, you'll get a different result. And then on Apple Silicon or Windows, like those FMA instructions can give different results because there's this internal state where it's a higher precision, and then the way that math it gets promoted to some higher precision varies by platform. So you just turn that off. And the performance, I think fast math is it seems to be a joke. Like I've turned it on, it didn't get any faster. So, but then it just wrecks your determinism. I'm like, why do we have this? And then the other thing you need to do is the C library. If you're calling cosine or sine or arctangent, you have the Windows MSVC C library. You have the whatever the one is on Linux or Mac. That's going to have a different implementation of those trig functions. So you just got to implement those yourself.
Okay.
Which is not that hard, really. And then one other thing that I can think of is there's some SIMD instructions you may be tempted to use. Like there's this fast reciprocal square root. And that's going to give you different results on Neon SIMD versus SSE2 or AVX. But if you do all those, you can get floating point determinism, and then there's right. So that's kind of the math side of determinism, but then there's another side to determinism that's important is the multithreading. Physics engines are incredibly sensitive to the order of things. If I'm stacking boxes, I'm applying impulse here, impulse here, impulse here. If I change that order, I'm getting a different result. And there's many things that can wreck that order. And with multi-threading, as soon as you take a lock or you spin and you let things resolve in different orders according to who gets there first, then you've wrecked determinism. So yeah, so you have to be very careful with how you're doing multi-threading.
But in Box2D, do you have both multi-threading and deterministic order for solving all these?
Yes.
How?
So one thing when I was doing this kind of deep dive on improving the performance of Box2D was like, I realized I wanted determinism at some point, and then I was like, okay, how do I get that? And what you can do is you could do a bunch of work and then sort the results, like single threaded or something. You just call qsort or something like that, and then you get your ordering. There's another way to preserve ordering that I found, which is quite incredible, is this data structure called a bit set. So bit set is, the way I represent it, is just an array of uint64s. So 8 bytes. And just a big array of those. And each bit represents the index of the body in my array of bodies or contacts or whatever it is. You can use them in these bit sets in several different ways. And the thing is, you can, let's say you have 8 workers and they're changing things, they're doing work. Each worker will have its own bit set representing all the bodies, say.
Yeah.
Okay, then there's a sync point where, okay, I'm back to single threaded. They've done all the work. Each one has their own bit sets. Now I'm going to take those 8 bit sets, because I had 8 workers. I'm just going to OR those together and resolve that to one bit set.
Oh, and no matter the order of the workers, because they were doing work here and here and here and here, and if you OR them, like no matter what was the order, the result will be the same.
Yeah, it always bakes down into the same order.
Okay.
And then the question is, okay, I got this bit set. I may have 1 million bodies or 1 million contacts or something like that. there are instructions for traversing bit sets, which make it incredibly fast to iterate across all bits. Even if there's 1 million bits, it can be incredibly fast. So you just use those intrinsics instructions, and you can go over those bit sets. And then so that recovers determinism with no sorting, because I'm going through things in order in my serial part of the code. So that's always the catch, is like, okay, I did a lot of work multi-threaded. I want to set myself up that when I'm going back to single threaded, I'm going to be able to get that single threaded work done as fast as possible. So I go back to multi-threaded.
That's cool. That's super cool.
Yeah, it's bit sets are, like, if you get into multi-threading, I recommend anyone who's doing multi-threading work, bit sets may help you. They may help you, yeah.
So what is the Box2D? You mentioned now 3.2 will be like the bigger release that you're working on now. Do you consider then Box2D more or less finished? Or because you have your other work and like other physics engine for the game that we still need to talk about, by the way. Like what is then the Box2D state in terms of the project? Like, is it finished? Is it not done? Will it be like worked on or another spring break some point in the future?
I think once 3.2 comes out, I'll probably do a minor revision or two to fix bugs or whatever. But yeah, I think it will be pretty mature at that point, and most of the main features that people want will be there. And it would be hard to make a game that would really push Box2D on performance. It would be hard.
Okay. And it's available open source on GitHub for everybody to see and use. Okay.
Yeah.
Nice. Then is this the point where we start talking about A Legend of California?
Sure, yeah. So in 2022, I left Blizzard and I joined some friends that made a startup called Kintsugi-yama. It took me a while to learn how to pronounce that, Kintsugi-yama. And this was kind of a very different experience from Blizzard. Blizzard, I had been in Blizzard for around 15 years, and Blizzard got to be bigger, and the way it operated kind of changed over time. And I had, from my Silicon Valley days, had some of that startup experience and I was kind of interested to get back to that kind of experience, the smaller, hungrier team. So I joined some friends that made this startup, and that startup, I think, was completely stealth for about 3 years, or maybe even more. The studio was unannounced. The game was unannounced. There was no webpage, nothing, for at least 3 years. And we're working on a game that's pretty crazy to have a game this big being made by a small team. Granted, we are around 35 people now, but the game it's a multiplayer game. It's not another PvP arena shooter, though. It's more of a open world survival game, survival action, MMO light type of game, and it's set in the gold rush era of California. And it's like this alternate history sort of thing, the games like BioShock, it's like kind of this alternate history. So there's this alternate history of California where California is an island. And it's kind of, and people apparently, early explorers of North America, thought that California was an island, or there was some like kind of legend that it was an island. I don't know why, but it was. Anyway, so imagine California is an island, and it's big. Like, it's not full scale, right? But I think it is roughly 20 kilometers from top to bottom. So
because of the limitation of the physics engine.
Yeah,
exactly.
Actually, I pushed for that when we started. I'm like, don't go more than 10 kilometers from the origin, because it wasn't just of course I didn't know all these optimizations I could do, but I think once you start having everything in doubles, it kind of get out of control, and now you're just doing a lot of expensive things. But the game world as it is, even with that size, it feels huge. So as part of that, we want to fit in a lot of players to kind of help fill that space. So that's a real challenge as well. So that's where I need a really high performance physics engine, not only just to support having a game world like that, but also I really wanted to have more kind of physics-based gameplay that's actually part of the gameplay. A lot of the Blizzard games that I worked on, like Overwatch, they had a lot of physics like ragdolls and breakables and things like that. Almost none of it has any impact on gameplay. And it's all like completely client-side, and it's just visuals. In our game, it's because you're kind of in the gold rush era of California, you're kind of trying to survive. You're chopping down trees. The trees have real physics that's on the server. There's animals that you hunt, and then you need to skin the animal. That means the ragdoll needs to be in the correct place. The ragdoll can't just be client side. So if you kill an animal and it falls off a cliff, you should be able to go down to the bottom of that cliff and then skin that animal or bad guy or whatever. And so we needed to have the ragdolls on the server. So all of a sudden, now there's a bunch of gameplay centered around physics or dependent on physics. And so if this stuff is running on the server and we say we have 100 players, hopefully, that needs to be high performance. There's no way around it. So that was kind of the impetus I had for, okay, I need to, what does Box2D look like at peak performance? Let me develop that, and then I'll bring that over and develop that technology for Legend of California. Yeah.
How do you estimate what kind of colossal physics simulation can happen if you have multiplayer game that can have hundreds of players, and now each of them is stacking boxes and then breaking walls and then like dragging ragdolls around and like pushing into the boxes? Yeah, how do you estimate? Like, obviously you cannot push it like too much. Like there will be a finite end for your physics engine, and at the same point there doesn't seem to be a reasonable way to estimate what's gonna happen.
Yeah, it was interesting you say that. We had an alpha test, and one of the players went on top of some mountain and then chopped down every single tree that they could find. And then the server was lagging.
Exactly.
Yeah, so I'm actually developing Box2D for this game.
Oh.
So it will be open source. It is like basically Box2D taken into 3D. And that's one of the wonderful things about working for this company, is that they have let me create this 3D physics engine as part of my job, but it will be open source.
Nice.
Yeah. And so it's part of when I'm testing that physics engine, like most of the time when I'm looking at performance, I'm looking at the performance of a bunch of trees falling. How can I make falling trees faster? And so I put a lot of mental energy into that.
How are trees simulated as a rigid body, but like, I'm assuming, but as a cylinder or as a sort of like more closely, more granularly?
So at first, I was like, oh, what if the tree is just a capsule? It's a single capsule shape, just an extruded sphere. That should be fast, right? But then our artists, they started making all these kind of curvy trees, and okay, well, that's what California has. It's like all these kind of different trees. And so what we settled on is the trees are represented as a kind of bunch of segments of approximate cylinders, like maybe like a 6-sided cylinder or an 8-sided cylinder, and they're just stacked up. And the reason that they're stacked up is because when the tree falls, it falls as a single rigid body. It's one rigid body, but it's enormous. It could be like a redwood, just like 100 meters tall or something crazy. But then you need to be able to chop it up with your axe. So each cylinder is that thing being chopped up. And then you kind of like, it's like cutting carrots or whatever, but like you cut up this tree, and now you have the section. Now you chop that, and then it creates a bunch of logs. And then you carry those logs back, and then you build your ranch from those logs. So all of that
is all simulated.
Yeah, that's all on the server, all simulated.
Wow.
Every player will see the same thing.
And like every player can do the same thing at the same time.
Right.
And this needs to be simulated. Okay.
Yeah.
Wow.
There's enough to do in the game that you're not just... I mean, maybe there could be an agreement on this one server. Hey, we're all going to chop trees at the same time. But a lot of it's, no, I'm doing some mining, or I'm taking on some bad guys or whatever. So...
Like your hope is that there won't be like a guild of pranksters who they agree that like at 7:55 they all go chopping trees or whatever is the most like extreme activity for the physics engine.
Yeah, there's some ways to solve this with design. You know, this is not a full physics sandbox. The player just can't create anything that they want. So like, okay, say they chop down 10 trees, okay? The 11th tree, they chop that down. Okay, you can chop that down, but the oldest tree, it's disappearing, right?
Decaying
something like
very
that.
Quickly, yeah, okay.
You get a quota, something like that. We also have it's kind of interesting. So we have all these ragdolls on the server, and those all kind of get networked. And the thing is, when there's like a dead enemy, you go get the loot off of that enemy. Once you've looted that enemy, that ragdoll's gone. It disappears, right? Because it doesn't need to be in the world anymore. It's only there as kind of like your place where you get your reward. So then that means the players are automatically going to clean up all these ragdolls. It's funny, though, because this comes up because we have automation. So we have all these bots that run around the island killing things. And at some points, like, they weren't programmed quite right, and they're just, like, leaving ragdolls everywhere. The whole island is just covered with ragdolls. And, like, people are coming to me, like, Erin, why are your physics so slow? Like, why is this, what's happening here? And I go and look at it, I'm like, okay, well, they're just, all these ragdolls is laying everywhere. Like, players are not going to do that. Players are greedy. They're going to want to get their reward. But, I mean, yeah, if they had some agreement to, like, hey, we're going to take down the server by generating a bunch of physics, yeah, we might have to take precautions.
Yeah. And maybe people are not aware, because like often when people play like single player games, you're expecting, for example, rendering to take a lot of the time, right? Oh, there's a slowdown, like you see choppy frames. It's because like your PC that you have locally is not keeping up. But if you have a networked game, the server is the one who needs to simulate everything, and clients can go further only when the server is done with the frame and can go to the next one. So server is the one that will be the most important for the entire game for the simulation to happen. And if the server cannot keep up, like nobody can keep up, like you can have, this is why you can do something on a client, and then after a couple of seconds your player's like boop, back to your old position, because server did not simulate that properly. So this is very interesting, because as you mentioned, like other games like in Blizzard games there were physics, but they were simulated on the client for the visuals, for the effects, and if you push more and more things onto the actual server, then this becomes interesting.
Yes, in our game we also do the animation on the server as well. This way, if we have PvP and you shoot another player, you can't just say to the server, hey, I shot this guy, kill him, because then immediately we're open to cheating. And so we need to have the animation on the server. And what's interesting is, so I see this other character animating, they're moving with their animation because that data is coming from the server. That pose, basically, we have a way to make it very compressed, but it essentially is like sending that pose. And if the server is lagging, you will see like the kind of like strobe light effect of other characters, like not, their animation gets choppy. And I actually love that, because I would never want to ship that. But if we're testing and we see, oh, this animation looks choppy, it's the server's lagging, it's like you can instantly know.
It's an immediate debugging facility.
Right.
Nice. So how do you approach the development of the game and physics for the game? How do you know what to work on next?
So there's lots of things that you could imagine in this kind of world. I'm in the gold rush. What could be physics? What would be exciting for the player? And what would be like make the world feel more tactile? So we knew early on that like, okay, yeah, we want trees. And then we introduced like skinning of animals, and okay, yeah, the only way to do that, we have to have the ragdolls on the server. And then there's other things that come up, like maybe we want things that are exploding, or other types of gameplay elements, like I want some sled to pull my logs around on, or things like that. And so a lot of this does come from like, sometimes it comes from like, well, we need this to solve this design problem. But sometimes it's, well, what would be fun? Is it feasible that we could do this and add this, that it's fun? So to get a lot of this stuff in the game, we have to work with our gameplay programmers and designers to get this all in. And so it is like a team effort for everything. And like the trees, like we have all these different kinds of trees, and they have to all be choppable. And that to me is kind of crazy. And we have a technical artist that just spends so much time just processing trees. A huge amount of effort has gone into just that experience, yeah.
Processing trees, meaning what exactly? Designing and making them, or?
So we have artists that makes trees in SpeedTree, and then those come into Houdini, and then we run further processing on those to generate the collision. When a tree gets chopped, we need to generate interior surfaces, so you're not just seeing into an empty space. So we need to see like, okay, yeah, I chopped here, here's this rough surface. The bark has been removed. All that visual stuff needs to be set up. And like you have to do that procedurally, because like we have like 100 different kinds of trees. Because it's trying to represent the ecology of like native California back at that time. So that a lot of games that have like the tree chopping, that some of them do better. Like we look at all the games that have tree chopping, right? Some games you chop a tree, the tree just falls straight down through the ground, and then some wood appears on the ground or whatever. Some games you can actually chop down the trees and they fall, but there's one kind of tree in the entire game, right? But now it's like, okay, no, this is art. We're going to represent all kinds of trees. So that's the thing about California that makes it kind of interesting for the game, is it naturally has multiple biomes. There's desert, there's mountains, there's redwood areas, there's all kinds of different areas across the island, and they all need to kind of look like you're in a different place, and a big part of that is the trees.
When people ask like, why games are so take so much time to make, like, there are people who single-handedly work only on tree processing. That's crazy.
Our technical artist, she spends a lot of time on the trees, but she does a lot of other things as well. We have rocks, you can break the rocks. We have all kinds of management of like, okay, I have this island and I need to have things spread out across this island kind of naturally, but it's got to be done procedurally. The thing about the game that's interesting, or one thing that's interesting, is that the world has a seed, kind of like Minecraft. And when you get a different seed, there's things that change. There is, across the island, there's difficulty levels, and those difficulty levels get remixed. So sometimes you start on this side, sometimes you start on that side. And then there are many different kind of encampments or strongholds that are placed around for different bad guys or whatever. And those are all get shuffled around. And then everything, when these things get shuffled around, that affects, we have roads that connect different parts of the island. Those need to move. Then all the plants and all the trees and all the grass, all the branches that you can pick up, all the little pebbles, they all need to adapt to that. So yeah, she works a lot on that system as well.
Okay. Do you have in mind also some cool systems that you'd like to highlight from the engineering perspective? It can be both on the game side, but also it can be on the tools side.
Right. So we work in Unreal, but it's modified quite a bit. We have our own physics, as I've said. That's Box2D. We also brought in a different animation system, because we need the animation to be on the server. And that animation system comes from an open source game engine called Esoterica that I worked with those developers, and they were kind enough to let me take their animation technology, kind of bring that into Unreal. So one thing that's cool about Unreal is you can develop tools in there. You can create your own editors. So I created a bunch of editors for this animation system and also for the physics. I can create a graph nodes in Unreal. I can write tools to preview animations. I can write tools to create ragdolls. I can do all of that. So that's my work. And then we have, on the gameplay side, we have a lot of custom code there as well. We have an ECS. So this group, a lot of the engineers from this on this team worked on Overwatch. On Overwatch, we developed an entity component system. And there was actually Tim Ford, our studio lead at Kensugiyama on the engineering side. He actually gave a presentation at the Game Developer Conference a while back about the Overwatch entity component system. And then that system kind of evolved for this game. So we do that. That really determines a lot of how the multithreading works. So any component systems, anyone's familiar, they kind of set your data up in a way that makes it more reasonable to do a lot of parallel for type of work. So that's pretty beneficial. And then we have our own. It's pretty wild for how small the engineering team we have, that we have all this technology, but we also have our own scripting, node-based scripting system that our designers interact with. And that scripting system also has like inspirations from what was done on Overwatch. And that scripting system is, what's cool about it is that you can write, or you can create this visual scripting system, and then it automatically gets networked in the correct way.
Oh.
And it also supports the client prediction. I'm like equipping my weapon. I'm changing weapons. I'm changing from my pistol to my rifle or whatever. The script can predict that. And that is
Predict what exactly?
It will play the animation before the server even says that, okay, yeah, you did actually equip that weapon, or you shot that weapon. And
but based on what can predict that?
Based on the user input, right? So the user presses some input, and then the script just runs ahead on the client.
Okay. But
then the authoritative state could come from the server and then correct what happened in that script. It can kind of roll back and say, no, you said that you shot, but you were actually out of ammo. Or actually, you were dead because something else killed you. And like,
but this prediction happens for your player character because you have only inputs for you, right? Like for other, okay. I was for a second thinking like, oh, it predicts like what other people will do. And then I was like, what the heck is this?
No. There is this other thing there that is relevant that we brought over from Overwatch, which is this idea of like, I'm shooting this character. I've lined things up, and I know I should hit this target, but I have latency, right? And do I shoot where the server thinks this character is? No, the server is going to help me out. The server is going to say, oh yeah, I see that you had this latency. You got 100 milliseconds of latency. So I'm going to, when I get your instruction to shoot, I'm going to move other characters back to where they were 100 milliseconds ago. And then I'll pose them with the animation that they had at that moment. And then I will do the raycast. And then I'll tell you, yes, you if you hit or missed. Yeah.
That's a lot of work, no?
Yes.
Like going back and this needs to happen every time you like trigger an important action, like shooting?
Yes.
Wow. Okay. So you're buffering the state for some time in the past, or you're just rolling back all the changes?
Yeah, it's like it's like half a second of history or something like that we keep for like 60 frames a second over half a second. We keep a buffer of that information for things where it's important. Okay, I'm shooting this tree, like, okay, I don't need to rewind this tree. But if I'm shooting another character, okay, yeah, I should move this other character back in time, play their old animation.
Wow, like the number of things you need to think about when you have this much physics simulation plus networking and all these kind of tricks, like the state, like people who just need to handle state complain like, oh, I need so much state to handle. You have like state from the past that you need to handle. Yes. and properly align from state from the present. And you have this spread across clients plus server. Like, wow. I cannot imagine how much headache you need to have on a daily basis. Or
yeah, I mean, I think about that a lot. Like, if you want a multiplayer game with high fidelity, you should be really sure you want to do that, because it's a lot of work. So you should know what you're getting into when you're like, okay, yeah, I'm going to make multiplayer. And then, yeah, you always hear about these games that they're like I'm going to make a multiplayer change to my game. I'm going to make my single player multiplayer. Man, it's really hard if you don't start at the very beginning. Like the first line of code is like network server.
Did you thought about this already when starting the project? I'm assuming.
Oh yeah, at the very beginning we knew we wanted to have a big player space. So the game is kind of interesting because it's mainly, at least the classic version of the game, we're going to allow for modifications or whatever, but the classic version it's mostly PvE. But then there are zones in the world like, okay, I want to go attack this encampment or stronghold where the enemies are. If I go into that zone, I am now flagged for PvP, and then other players can join in the mix, and it's just all out war. But you don't have to go there. So that's the thing. It's like you can make a choice.
You can live your comfy life without that.
You could spend a lot of the time just fishing if you want.
Nice. So the game Legend of California is set to come out in the fall this year. Is this correct?
No, we don't have a release date just yet.
Okay.
We are in the middle of alpha testing. We just had our second closed alpha, and I imagine we'll have a couple more. It's like you alluded to, having a lot of players with all this stuff, it can be quite a load on the server. So we need to bring down the memory, get the performance good. I also didn't even mention we have voxels. Like the whole world is voxels. So you can, on your ranch, you build your own ranch, you can build your own buildings, and then you have your own mine, and you go into your mine down 10 levels deep, and you can dig that out. So all that world modification needs to be networked, and it needs to live on the server.
How did the playtests go then?
So we've had 2 alphas so far. The first alpha, I'd say we weren't ready. We had tested things at scale. We had tested, I think, around 60 players or so previously. But there were things that we didn't account for. For example, you could have a server that maybe only 60 players are in the server, but there may have been hundreds of players that actually had logged into that server at some point. And maybe they put down a tent, or they made a ranch or whatever. They had an impact on the world, and that impact on the world that they made is still there, and that's still, the server still needs to have awareness of that and store information about that and network that. And we did not account for that. And so it ended up using way more memory than we expected. And so we got through that alpha. We kept the servers going. We did have to reduce the player counts a bit. We got through it. People had fun. Performance was not good, not great, not great. So we took a couple months and okay, we got all this logs, we got all these information, we got all this data. Let's build more bots, do more testing, more automation. And then let's look at where is all this memory coming from? What do we need to optimize? And so, the team was just hunkered down for a couple months, just optimizing things. And so we recently had our second alpha test, and that the performance was much better and the memory usage was much better. We're not done yet because I've been really getting into this, let's get all the information out of the server. How can we visualize all the information? Let's make bar graphs. One thing I found is in the game, there's these little rocks you can pick up because I need a stone to build my stone pickaxe or whatever. So all these little rocks. And usually you think in a survival game, well, I started on the beach and, okay, yeah, there's some rocks there. I picked them up. But then I was generating logs and creating bar charts, and I was like, oh, we have 300,000 little rocks all across the island. And that's because they were just everywhere. They weren't just like on the beach. They were just everywhere. You couldn't walk more than 10 meters without tripping over one. So it's like, okay, let's bring that back down and let's save some memory, save some performance, things like that. So yeah, you have to really know what is all the data on that server. What is it doing? It has to justify its existence. Like everything on the server has to justify its existence. Yeah.
What have you found useful for this kind of process? You mentioned like generating charts. Also, I guess you have logging, right? So you can get information like from the textual format. Do you also like have some sort of bespoke tools for visualization? Like what works best in your case?
There's a lot. Yeah, I think you want to kind of do all of the above. So we have for our game, because it's kind of a persistent world, we actually have like a small database that stores the state of the game world. So we can take a game world that already exists and then spin up a server on that game world. And then we can look at, there's tools that Unreal provides. There's a memory insights, which lets you see, okay, this is all the memory. Sometimes it's still kind of opaque and you don't know really where all that memory is coming from. So that's one angle, is just attack the memory. And then so we have some data structures that I'm responsible for on the team, which are the data structures that kind of organize everything spatially, like all those little rocks, all the branches, all the feathers, every little thing. That's kind of like my data structure that the team is just putting all the stuff into. I'm like, okay, let me just grab that data structure and everything that's in there, I'm going to just go over and say, okay, where are you from? What are you? Oh, you're a leaf? Okay, you go in the leaf bucket. Oh, you're a branch, you go in the branch bucket. And so I just get a tabulation of all those things. And then all of a sudden it's like, okay, yeah, I just counted 300,000 little rocks. Okay, and so I just have some JSON and some HTML and just draw a graph. Yeah.
And you mentioned that the worlds / servers are supposed to be persistent, meaning like if a player logs in, goes to a mine, like removes 100 levels deep down into the mine and then logs off, like this is a persistent change on the server. And I had a friend who worked on a game that tried to like had these worlds being simulated for a shorter amount of time to sort of have less of a problem, an issue with just like keeping all this stuff around. Do you have any ideas on how to ensure this long living lifetime of these things?
Yeah, so that kind of gets into the design, and you kind of need the design to help out where your tech kind of hits its limits. So there are some survival games where, like, if you join the game and you play for a couple hours, but then you don't play for a month, your stuff just kind of like starts to leave the world. Your tent kind of gets ragged, then it disappears, things like that, or your mine kind of fills back up. So I think that's going to be a thing. Also, the game design is that the game will reset on some regular cadence on the scale of a month or 2 months or something like that. I don't think we've nailed that down just yet, but yeah, it's not going to go on forever. Like if you think about like, oh, this is game where I can dig voxels and I can chop down trees. Like after a couple months, there's going to be no trees and the entire world is dug out, right? So what kind of game world is that, right? Nature needs time to heal.
Exactly. You could think of like having for every process, have an anti-process. So if you chop down the trees, they're also like trees grow back up. And this like constant fight of trying to like keep this in equilibrium. But I guess it would be very difficult to really like for every little action that people can have in the world to have the same response.
Yeah.
Nice. So people can wishlist Legend of California, right?
Yes.
It's on Steam.
Yes.
I don't know. I don't want to like cause you to spoil any sort of or tell any information that you're not supposed to. But are there like other platforms announced yet? I know it's on Steam.
Our plan is we're not going to consider other platforms until after early access. So we're going to be an early access game. And then I think we will consider other platforms once we go to the final version. Yeah. I think for a game like this, early access seems to make a lot of sense, but we are going to try to have it be like a game you can really enjoy even on day one of early access and get all those performance and memory things sorted out before then. So that's really kind of like the team's big focus right now is making sure that early access experience is great. And then I also encourage you, if you go to kensugiyama.com, there's a link to our Discord. Join the Discord if you have questions. If you're interested in getting an alpha test, you can sign up for the alpha tests on Steam. Also, involvement in the Discord channel can help you out there if you're interested. Yeah. And our Discord channel is great. There's lots of great feedback there that we get. So
both Steam and Discord channel for Legend of California. Awesome. Yes. Awesome. Erin, and where can people follow your work? For example, Box2D and maybe Box3D in the future.
Yeah, it will all be on the same website, box2d.org. And then lately I like to give updates on YouTube. So I'll update YouTube as short little videos of, check out this feature I worked on. And they're pretty informal, but I think it's a great way to share because physics is just so visual that I like just to share those visualizations. Yeah.
Awesome. Erin, thank you so much for joining me.
It's been a pleasure.